Okay, cool. I did too. My question. Yeah, like, It's crazy.
So it's 7:30 and we start and just for reference, this is going to be our last lecture on chapter 2. And we're going to be starting chapter 3, which is computer arithmetic on Monday. And we're going to start with a review of binary numbers. But we'll check the end slides. I don't think I have any readings for you guys to do on Monday. So we've talked about what performance is, some different performance metrics. We'll talk about one other performance metric that is not really used. And we also talked about how to evaluate performance with the CPU time performance metric that we talked about before. And then the three things that go into CPU time, which are instruction count, CPI, and cycle time. And we're also going to cover now power trends and also their implications with CPU design. And common pitfalls is Amdahl's law. So like we just talked about, we talked about these different hardware and software components and how they affect those performance metrics. So the algorithm that you write in your high-level programming language is going to affect the instruction count, right? Basically, the worse your algorithm is, the more instructions it will require. And then you can also affect the CPI by affecting the instruction mix. So if your algorithm is very inefficient with memory, then you're going to have more memory instructions, moving data in and out of the CPU, and higher CPI. Programming language that you use can also affect your instruction counts and CPI. So Java is a very heavy programming language. You do no memory management yourself, right? But it comes at the cost of being memory inefficient. It's its own garbage collector, and that will affect the CPI. And then that also affects instruction counts because there's going to be instructions added in that you're not exactly controlling. And again, your compiler. So your compiler can be very bare bones and just directly translate your high-level code. But some compilers have better optimization. So we had an example in the last lecture. We were saying the compiler was choosing between two different paths. So that could be some kind of optimization that compilers do. So again, it affects instruction count, CPI. So essentially anything on the software side is going to affect instruction count, CPI. Software side is not going to change the microarchitecture, change the cycle time. But the instruction set architecture, depending on if it's RISC or CISC, can affect the instruction count, right? So if it's RISC, it's most likely going to have more instructions. Whereas if it's CISC, you have more complex instructions available to you. So you can do the same task in a smaller amount of instructions. And then your implementation of the instruction set architecture can change the clock rate or cycle time. And this is what we'll focus on in chapters 4 and 5. And then your instruction set architecture can also affect your CPI. So depending on what are the types of instructions that you have, how it's going to be implemented in hardware, what is the CPU that is being made going to try and optimize? What is it going to say, this instruction isn't really used all that often. I don't have to optimize for this. Things like that. So any questions on these? We're clear on all of these different aspects, why they affect these different performance metrics. We awake?
Probably.
I know we're 7:30. Alright, so power trends. And we're going back to the 80s with these charts, and ending in the 2018. And so the first thing that you can notice here is the blue line is clock rates, the black line is power, and power is highly related to your clock rate or your cycle time. And we increased very rapidly, and then we've kind of hit this flat line and wall. And that's because we've run into this practical limit for the amount of cooling that we can put on a small package. So we couldn't increase clock rate any further without frying the silicon. Okay? And if it gets too hot, then your cycles are not going to be precise. You're going to have some errors in your compute. And if you have errors in the compute, then you don't really have CPU anymore, right? All right, so here is processor performance. This is also using a different performance metric, but it's decent enough to compare these processors and plot them over time. And going back to, again, late 70s, early 80s, we can see that our performance has been increasing steadily year over year. 25% of performance per year early on, and then around 50% performance per year throughout the late 80s to the early 2000s. Then we're getting a quarter faster, then 10% faster every year, and now we're kind of stagnating. Okay? So one of the reasons that we're stagnating was this power wall, but the other reason is technology nodes. So technology nodes is basically how small the transistor is. And we're to the point where the size of the transistor is so small that its behavior is becoming unpredictable because it's only a few atoms wide. We're at trying to reach 3 nanometer process technology, but that's basically the limits of silicon. So basically the way that we're getting performance nowadays is not through improving general purpose computes, it's through creating accelerators. So you've heard of Google TPU, that is an accelerator. We're also using GPUs more often now in data centers as well. So the trend seems to be that, of course, we'll always have general purpose computes because we need to be able to have programs that do anything. But for certain applications, if performance is a key metric, accelerators are now the way to go. All right. So how did we get this in performance though? So there's many different ways. And we'll talk about this briefly, and you guys will also look into more ways that performance was increased with the research project. But that is towards the end of the course. And one way that you all should know, probably know about, is multi-core processors, okay? So the more than one processing core per chip, okay? And the thing with multi-core processors is that in order to take advantage of them with your programming, you need to write parallel programs. And most people still don't write parallel programs. Okay. So we can take advantage of this instruction level parallelism in our programs with multi-core processors. And this is kind of hard to do because of balancing and synchronization. Because eventually, if they're all working on the same task, they do need to converge and combine all of their results in the end. So now we're going to talk about some other performance things. So benchmarks, they do exist, and we'll talk about one very popular benchmark set that is used in research. And then after that, we'll talk about Amdahl's law with the performance pitfalls, as well as another performance metric, which is MIPS, not to be confused with the instruction set architecture MIPS. All right, so one thing that you might look at when building a computer is like what CPU to buy, right? So on the consumer side, mainly like media publications that you would look at are using benchmarks to compare these two products. Okay. Basically, a fixed set of standardized programs that run on both of these processors. So even though the microarchitecture is different, they're doing the same task, essentially. And it's convenient for these two because they both use x86. But some benchmark suites exist where they're compiled for different architectures as well. So here's some examples of like published benchmark results. Like here's from Tom's Hardware. And then here's a benchmark running Blender. So this is Blender is rendering a classroom. And then there's a Cinebench and it's V-Ray. So these are standard benchmarks that are used in media quite a bit. And you can see all of the different processors that are comparing across generations as well. Right. So these benchmarks, they are programs used to measure and compare performance. And they're supposed to be typical of an actual workload. So some benchmarks are actually just a real workload, like the classroom example is a real workload. But some are synthetic, like Cinebench is. I believe V-Ray is also synthetic. But Microsoft Excel, it's a real Excel worksheet. So this is going to be particularly important for CPU design as computer architects need to make trade-offs in the microarchitectural decisions on what to optimize. So they need to know what is the real workload so that we know what we should optimize. And then the other thing about benchmarks is that reproducibility is very important. Because if you cannot reproduce your results with precision, then you can't really compare results, right? So there's lots of different parameters that are going to running these benchmarks on like the consumer side after the CPU is already made. So they affect performance quite a bit. And that's why I mentioned beginning, the computer architects are not really using these benchmarks the same way that consumers are. They are doing strictly CPU time. Okay. So these benchmarks, when you run them on the CPU, you have the operating system scheduler, your different storage mediums, and the disk, all of these things. Are other things running at the same time? So because of that, computer architects focus on just CPU time. All right, so here are some very popular benchmarks. But the key one that we are going to look at in a little more detail is spec. So spec is the one that I want to look at for us, is because that one, the benchmarks are relatively small and they are used for simulation and strictly looking at CPU time for research papers. And Intel uses this as one of their guidelines for did performance actually increase. And spec is always being revised and adding new benchmarks. Like they've added floating points, some protein folding, lots of different applications are being added to this spec benchmark. And the other thing is it's a standard performance evaluation. And it's based off of real programs, like I mentioned. And it can be indicative of performance for the CPU, but it's also input outputs, and it has web applications, memory, and it's been kind of evolving for a long time. And you can find the kind of set of spec benchmarks labeled by the year, so there's spec 89, spec 2006, spec 2010. Okay, so in spec 2006, here are the benchmarks that are inside of it. So they have Perl bench, which is, I believe, just a compiler for Perl. And then they have compression. They have a artificial intelligence benchmark, chess. They have a quantum computing benchmark, video compression. So all of these are just strictly integer though. And then they have this whole set of floating point applications as well. So fluid dynamic simulation. There's 2 fluid dynamic simulations. And then quantum computing. All of these things. And spec after 2010, they are also releasing GPU benchmarks. And then this is just the performance on different benchmark sets for Intel chip. You can see they were reporting the CPI, the instruction count, clock cycle, everything that you need to calculate CPU time. Okay. So this is the pitfall that you guys read about. So Amdahl's law, the pitfall is that we expect improvement of one aspect of the computer, say CPI or cycle time, to increase overall performance by an amount proportional to the size of the improvement. But in reality, the performance improvement is limited by the amount that the improved feature is actually used. So an example, the example is in the next slide. That's here is kind of why that is the case, right? So this is the portion of the execution time that is actually affected by the improvements. So the time that it was before, and then divided by the amount of the improvements. But then you still have this whole other section of execution time that's unaffected because it was not improved by the improvement. Okay? So if this is like 90% of your execution time, and you only sped up 10% of it, even if you made this 0, you've only become 1.1 times faster. So Amdahl's law is useful to estimate performance improvements when we know that the proportion of time consumed for the function that we are trying to do speed up for. And you can also argue those practical limits for something like the number of practical. Because you can split up the execution time to how much of it is parallelizable, how much of it is sequential. So if you're 50% parallelizable, 50% sequential, no matter how many cores you have, your maximum theoretical speedup is 2 times. So here is an example. So a company is looking to enhance a processor for web serving, and you're running a benchmark that takes 100 seconds to run on the processor, and the processor is busy with computation 50% of the time, but waiting for input output 50% of the time. So by how much is the total time reduced? The computations are made 2 times faster, right? So again, here's our equation. Execution time affected divided by the amount of improvement. But you have to add back in the execution time that is unaffected. So 50, because it's 100 seconds total. So 50 seconds is compute, 50 seconds input output. We made this 2 times faster, but we did not affect this. So overall, our new execution time is 75 seconds, which is just a total reduction of 25%, or a speed up of 33%, 1.33. Right, so we made computations 2 times faster, but our overall performance only 1.33 times faster. So then the question is, by how much should you improve the computations to get the benchmark to run 2 times faster? Well, again, using that same equation, we just put n for the amount of time that we need to improve by. If we solve for it, it's impossible, right? You can't make it 2 times faster. It's at the limit of, because we're not improving the input output. So even if this becomes 0, we're not there, right? So Amdahl's law is very useful to help you guide, like, what should I actually be targeting? What is the piece of my program or piece of the microarchitecture that will give me the best performance improvement because it's used the most? Okay, so here's another example. When you're trying to analyze if adding more cores is beneficial or not, your program is able to be 80% parallelizable. And overall, it runs in 100 seconds with a single core. So what is the execution time if you use 2 cores? And they're assuming there's no overhead for like combining all of this back together. So same equation, right? So we have 80 seconds that's parallelizable, 20 seconds that's not. We have 2 cores and no overhead. So we can have 40 seconds for one core, 40 seconds in the other core, and at the same time. So overall, this will become 40 seconds plus 20 is 60 seconds. Okay. And here is your checkpoint question. So what if we use more cores? Question. What is the execution time? And your code is 979. Don't see any new responses coming. So, does anyone still think about this? So we are well past threshold. We have 93% of respondents getting the right answer. So anyone want to tell me what they answered, how they got there?
I chose B, but I used the same equation as last
Yeah.
time, except substituted 4 instead of 2.
So if we go back to the same equation, same setup, because it's the same 80% parallelizable. So 80 and the n in this case, or amount of improvements, would be 4 because we have 4 cores. So all 4 of them can work at the same time. So 80 divided by 4 is 20. And then plus 20, it would be 40, which is B.
What does it mean when it's 100 minus 80?
Because we have 100 total, we're not explicitly told that, we just know that 80% of it is paralyzable. So 80 seconds is paralyzable, and then the leftover is 100 minus 80. Yeah. So here's another exception to this. So we're still 80% paralyzable, 100 seconds total. The question is, what is the execution time if the program was only 10% paralyzable? Then we're only seeing 5 seconds save. And then 7.5 seconds save. Okay. So there's no real speed up that we're getting from multi-core if it's only 10% paralyzable. So maybe it's not worth the 5 times more time used to program it to be paralyzable. Right? Maybe it would be better off if you use your programming time to optimize the single-threaded performance. So from this, we get one of the core principles of computer architecture, and that is make the common case fast. So the case that is used most often, we're going to optimize for that. And this also comes back to RISC versus CIS. It is a lot easier to optimize on the microarchitecture level, very simple instructions. And if you have very simple instructions, they are going to be used very widely. So when you make an optimization for that very large, simple instruction sets, you are affecting a lot of your. Whereas if you have a complex instruction that does, again, matrix multiplication in one instruction, but how many applications out there are going to use that instruction? We're not going to optimize for it. So that's why RISC can be a little bit better than CIS in some cases. So some other examples of this. So all instructions need to be fetched from memory, but only a fraction will require a data fetch of getting like real data, so load or store. So we're going to optimize instruction access over data access. Another example is programs spend a lot of time accessing memory and exhibit spatial and temporal locality. We'll talk about this more in the memory chapter. But that's why we have a storage hierarchy. We already talked about the storage hierarchy. So the other common pitfall is that thinking one or subset of the variables is indicative of performance when it is really not. So this, by variables, we're talking about CPI, instruction count, and cycle times. Whenever we're evaluating performance, we need to make sure that we check all 3 of those things. We can't just say that we improve CPI by 2 times, so our speed up must be 2 times. All right, so here is the other performance metric that we should talk about. This was used, it was mainly used in research articles a long time ago. It's kind of faded out because we realized that it's really a fake number. But it was still used in like marketing material for quite a while. So MIPS is millions of instructions per second. So this is just take your instruction count, divide it by 1,000,000, and then you get your clock rate and how many instructions you can do, how many millions of instructions that you can do per second. So one thing is, this does not account for the capabilities of an instruction. So like CISC versus RISC, RISC instructions are very, very simple, but they do not do as much as a CISC instruction, right? So we cannot compare computers or microarchitectures that are implementing different ISAs with MIPS. Because the instruction count for a RISC set is just going to be much larger than a CISC ISA. And the other thing, well, that just goes back to what I just said. But yes, we cannot compare different programs on the same computer because these programs also have a different instruction mix. Okay. Because of those different complexities, and that's going to give you a different CPI. Okay. So MIPS is not very indicative unless you're comparing same program, same ISA, just different microarchitectures. So it's very niche, right? Whereas CPU time is universal. So here is an example of using the equation. We have 1 billion instruction program, 3.2 gigahertz computer, 1.2 CPI. What's the MIPS rating? And if we plug everything in, we have instruction counts, and then we have instruction count, CPI, clock rates, and then we have this division by 1,000,000. So we get 2.67 times 10 to the 3. And here is a checkpoint. So again, do this on your own first. Have the equation. The question is just which has a higher MIPS rating, and then which is faster.
CPI, CPU time?
No.
Keep getting confused with that.
CPI is a component of CPU time, but it is not CPU time. So this is your equation for MIPS, and then your equation for CPU time, which will help you determine which one is faster, is instruction count times CPI divided by clock rate. Still working on this. And looking at the survey results. We are again past the threshold and it doesn't seem like we need to do peer instruction. So let's look at this example. So here's the same table, right? First question is which one has a higher MIPS rating? So here we have our MIPS rating. So if we look at the equation, plug in everything for A, we get a MIPS rating of 4,000. If we plug everything in for B, we get a MIPS rating of 3,630. So A has a higher MIPS rating, right? But if we plug in all of our values for our CPU time equation to figure out which one is actually faster. So again, instruction count, CPI, clock rate, divided by clock rate. Or if it was given as cycle time, multiplied by cycle time. So we plug in all of our values. CPU time of A is 2.5 seconds. B is 2.2 seconds. So A has a faster, higher MIPS rating, but actually slower than B. So higher rating, slower than B. So it is B. So we can see how this MIPS rating not always helpful. Yeah.
Because you said B was faster, not slower.
A has a higher rating, but A is, so A is still the subject. So it's slow. Yeah, it's no problem. Right. So the other thing that I wanted to talk about MIPS is I did mention it was used in marketing material. So what they put for marketing material is kind of funny. So MIPS, more instructions. You want to make the number look a lot higher, right? So easiest way to do that is make a program that is just all no operations. Right? So it's just proportional to your clock rate. They don't do this anymore. So something funny. But concluding remarks. So cost of performance is improving because of the technology development, both with microarchitecture and technology node, so how small the transistors are. And then performance is going to be specific to a particular program. And we would get the CPU time, which is our performance, which is instruction count times CPI times cycle. And then performance can be improved with program enhancements. So this is like your algorithm or things like that to lower instruction counts or get a better CPI. And then compiler enhancements can also lower CPI or instruction count. And then improvements in the microarchitecture can also lower CPI. And then we can also make improvements in microarchitecture to target clock rates. But again, these things are usually opposing. So if you increase your clock rates, usually you're going to increase CPI by a little, but sometimes it's worth it. And you wouldn't make the change unless it was worth it. Okay? And same thing with lowering CPI. Sometimes it can make your clock rates a little lower. So because we did no peer instruction, we're going to end a little bit early today. And the other thing that is a concluding remark is power is a limiting factor. And we can use parallelism to further increase performance if the program goes parallelized. So in terms of reading, there is no reading due before Monday. But all of your readings for next week, I believe there's only one for Friday, because Wednesday is also going to be review. But I can always just check on campus to double check what I say.
Piazza, right?
If you have any questions about it, yeah, yeah.